Hello. This video is going to be something different. It's going to be more about trajectory planning, and I would say that it's going to be like a combination of gearing and maybe alpha, beta, gamma filter techniques. Let me show you what I'm trying to do first. What I want to do is I want to get my actuator or motor, hydraulic cylinder, whatever, which is this blue line, to synchronize up with this red trajectory here. And I want to be able to do it smoothly and then be able to follow it. In a way, this is kind of like having a lineman trying to chase a back after like a kickoff, and the lineman cannot run directly at the back because the back will run around him. The lineman always has to move sideways and try to anticipate where the lineman's going to go, and that's the same kind of technique that I'm using here. So what you can see is the red line would be kind of like the runner, and then this would be the guy that's trying to tackle the runner, get in sync. But the way that I do this is that I generate a target position, velocity, and acceleration, trying to follow this reference target velocity and acceleration. And from the error between the two, I generate a jerk. That's this green line here. And that what I do is I integrate the jerk, and that will give me the target position, velocity, and acceleration. And I've got several of these already configured up, so all I have to do is just change this number here. See, it takes a while to do the calculations. And in this case, you can see the reference. That's what I'm calling what I'm chasing here, and you can see that they're in sync. So now that you know what I'm trying to accomplish here, let me just go on and explain a little bit more. Because what I'm doing is, like I said, I'm trying to minimize the error between the target and reference position, velocity, and acceleration. So this is the velocities. So this is the reference velocity, and then you can see that the target velocity has to go fast to catch up with it up here. The control output, the jerk, is going to be the same. When they get in sync, you can see that the velocities are matching perfectly. And then this is the same thing with the acceleration. So this is the constant acceleration, and because that curve is going like this, it's negative. So that's why the acceleration is negative here. But the target has to accelerate positive to catch up with it, and then it has to get back in sync. This is the error between the target and actual position. No, the velocity. Oh, this position and velocity. So the red is the position error, and the blue is the velocity error. And you can see there's a huge error to begin with between both the position and the velocity, but the velocity error goes to zero. That's the blue line, and the position error goes to zero when they get back in sync. And one of the things, I'm going to get to this time constant a little bit later, but how I calculate it. But basically, I'm using a time constant is to get to that changes the poles that allow me to minimize the error. And but what's different about what I do compared to what most people would do with a filter is that the time constant is a constant. And in my world, time constants aren't really time constants. The instantaneous time constant, if that's what you want to call it, that is something divided by the rate of change of something, like the velocity divided by the rate of change in velocity. And that could be an instantaneous thing. So if you have a differential equation, you would have e to the minus, then you would have like a velocity over, like a delta velocity over delta position times t. And that position, the velocity and the position would always be changing during the motion profile. And then the final thing I do is I generate feed forwards. Because I have a target position, velocity and acceleration, what I really need is the velocity and acceleration. And then I already know what the jerk is going to be. what I do is I can calculate out a feed forward for the PID and or in addition to the PID, but if the feed forwards are accurate, then the PID is going to do very little. And I don't show the PID part here, but I do show what the feed forward calculation would be. And here you can see that because it has to go forward to catch up, and then as um, the reference goes in a negative direction, you can see that the output here has to go down in a negative direction too. So that is what I am trying to do. Let me just show you one more here that so you can see an example. I try to save time by having all my things pre-generated. Now this is a pretty simple example. And let's go try a different one. Well, this is kind of like the number 2, only that's not quite as sharp. Now, what I have done is I do have position and velocity, or yeah, position, velocity, and acceleration limits and jerk limits. So that will you have to have these limits because the actuator may not be able to go at well, it just can't go at infinite velocities and accelerations and jerks. So now let me just go up to the top and show you how I'm doing this. Okay, this is my table of pre-generated problems, and that way I can change the parameters fairly quickly so I don't waste time. Now, one of the key things I have to do is generate a time constant. And like I said, one of the most important things is to generate a time constant that is changing. So the time constant isn't really constant. And what I'm doing is if I take the error is the error in acceleration. Here, this is the error in velocity. If I take the error in acceleration divided by the maximum jerk, then I get a time constant because this is like a position over seconds squared, and this is a position over seconds to the cubed. So when I divide that out, the unit is going to be time. And this is the same thing, except for I'm using the velocity and the acceleration. And here I'm using the jerk and the acceleration, but because I'm using the square root, it takes the 1 over the time squared. That's the the result, and then I take the square root of it, so I just get a time. So what I'm doing is I'm calculating out the maximum of these 3 different errors to calculate out a dynamic time constant. And this is some failed effort to calculate out a dynamic time constant. But given the current error, this is the error in position, velocity, and acceleration. This is the time constant, that instantaneous time constant. So now we got a time constant, and now let's use the jerk to update the PVA. That's the position, velocity, and acceleration. That's a kind of a symbol that I used for the position, velocity, and acceleration because there's usually a vector position, velocity, and accelerations, and in C I type it as PVA. So this is the position, and then what I'd want to do is I'll take a jerk and apply it. And then this is going to be it's going to return a vector of position, velocity, and acceleration. So this is the equation for the position. And this basically is using the old position to update the new position, assuming that nothing is changing, but we are changing the jerk. So this is the equation for the position here. And this is the equation for the velocity, and this is the acceleration for the acceleration. So the acceleration is whatever the current acceleration happens to be, modified by the current jerk times the time increment, which is 1 millisecond here. The rest of this is just applying limits. And in that table above, I have velocity and acceleration limits. And the reason for that is that to be realistic, you just can't be accelerating at infinite numbers. So for instance, even if you're lagging way behind, the target's way behind the reference, it still might be limited in the speed at which it can get to the reference. So let's find the this is my target generator. This is using data from above. So I got my reference position, velocity, and acceleration. So this is generating the position, velocity, and acceleration. And I have a noise generator here, which I haven't shown yet. And this is one of the reasons why you want to use this technique, is because it does kind of filter out the noise. And that's why I said it's kind of like an alpha, beta, gamma filter. And this is exactly, um, well, it's pretty close to what an alpha, beta, gamma filter happens to be. So what I want to do is I want to have the error between the reference and the target decrease using three real poles. And the three real poles are, you want to have that on the negative real axis, so I've got them real. That way I don't have an overshoot. And I have them at negative 1 over t. Now, normally I call 1 over tau the lambda right here. And these two equations are equivalent. They're just, one's kind of the inverse of the other. I did this simulation a long time ago, probably before 2010, and I was probably using time constants at that time instead of frequency. So this is calculating out the dynamic time constant, and this is what calculates out the jerk. So these come from this equation here, and then this is the target position, velocity, and acceleration. This is the reference excuse me. This is the reference target velocity and acceleration, and this is the target position, velocity, and acceleration. And I have to limit the jerk to something reasonable, whatever the the system, the actuator is capable of. And then it returns a target position and velocity and acceleration and a jerk. And I initialize everything so the position is going to be at 0, or the initial state is going to be at 0. And then I can change this. This just changes what column I'm using in the in that table above. So here, let me just kind of go up a little bit. It doesn't want to go smoothly. Okay, so I got my X min, X max. Okay, that happens to be my, in this case, it's my position, minimum and max. Then I got my maximum velocity at 50 inches a second, and my acceleration at 100 inches per second, and my jerk at 1,000 inches per second cubed. And you can see that the control output is maxing at, the jerk is maxing at my 1,000, which is this limit here. And let's go down below here and see. You can see that the velocity has maxed out at 50, and my acceleration is maxed out at 100 inches per second squared. And that's why this is taking a little bit longer. But you can see that the output, the jerk, is maxing out, and then it does nothing while we're at a constant acceleration. And then it goes negative to do this braking that's necessary. And then it gets into sync, and then the jerk goes to 0 when it gets itself back. There's no error between the reference and the target. So this is a good example of a motion profile with the limits being applied. So why do we want to do this? Well, one is that if you want to follow a reference, say you had an actuator that's trying to follow a reference from a joystick, the operator could be moving that back and forth, and you would need to be able to lead the operator a little bit, and that's what why I'm using the error in the position, velocity, and acceleration, because this allows me to lead the reference so that I can get in sync. If I just used a PID to follow the reference, what would end up happening is it'd always be lagging, and we don't want to do that. So, to make it so that they get in sync exactly, that's where you want to use the position, velocity, and acceleration, and the error between the reference and the acceleration and the target. So other options that I have here is I could use Butterworth type constants, And what I don't like about Butterworth type constants is they're going to overshoot. And let me just show you that. I made it so that I can just copy and paste these things so that I don't have to waste time. Let me, okay, now I'm using Butterworth constants. So these poles are in the same configuration as a Butterworth filter, 3-pole Butterworth filter. And let's just look at that. And you can see that it gets in sync pretty well, but it overshoots a little bit, and that's because the Butterworth has filter with 3 poles, got 1 real pole and 2 complex poles. And the complex poles will have a sine and a cosine component to them, which means you're going to have overshoot. But you can see it does a pretty good job of getting into position. You can see that the velocity overshoots a little bit, and you can see that the acceleration definitely has problems. Now, a good option, and a little bit faster option than using, let's see, where did I put that? Than just using the 3 real poles, is using an integrated time absolute error coefficients. And if I have a video on integrated time absolute error, but basically what it's doing is it's a time-weighted error uh, between the reference and the target. And I'm taking the absolute value of the error, and then I'm trying to minimize that, and I get these coefficients. And if you look up integrated time absolute error, you can see that these are the constants you get. And then you have to scale them based on the time constants or lambda. And I got a video on that. So if I copy these, and this would be the other alternative that I would use. And you can see that it does a pretty good job of getting into position. And I think it will even get into position a little bit faster than the 3 real-time constants. Let's look at this. Velocity does well, and the acceleration does well. But you can see I'm limited here by the maximum velocity and acceleration. So let's try a different one here. Let's try this original. And you can see that the integrated time absolute error coefficients, they work well. And here you can see that it has a little bit of overshoot, and that's because the integrated time absolute error coefficients do not place all 3 poles on the negative real axis in the S domain. So there are 2 slightly complex poles. And you can see there's a little bit of difficulty in here. But overall, I think that let's just take a look at how long it takes to get into position. And you can see that it takes about 4.5 seconds, 0.45. And if I come up here and go back to my 3 real poles, this will take just a little bit longer. You see, that's about 0.6. So you can see that the integrated time absolute error is much better if you need to get to the reference quickly. Excuse me. But you can see that there is a problem with overshoot. Anyway, I hope that you can find this an application for this, and I hope you enjoy the video. Give me a like if you can. I'll see you in another video coming up soon. Bye.